It's 2 o'clock. Let's get started. So today we are going to continue our discussion. So let's go to 365, table of contents. So we are sci-fi. We've covered Onyx already, so you're all set for the project. You should have everything you need there. Today we are actually going to talk about transfer learning. Um, and then we just have a few things. This is kind of what I'm gonna next Monday. It's kind of our last lecture. So I'll remind you, we are on week 14. So this week, today we're doing transfer learning. Wednesday, we're going to continue the competition, wrap that up. For those of you that already can finish stage 2, you can present, but that's due a week from Wednesday, right? And today I'll give you some code for that, and we'll go over some of the ideas. So next week, then we would wrap up with these topics on supervised learning and the XOR problem, right? So those are final topics. Anything else that I have time for? And then, so this is week 14. Then week 15 on Wednesday, I'm going to give you some time to work on your term project. Okay, and you can show me whatever you have if you have questions, etc. Your Onyx project. Does that make sense? As well as stage 2 presentations. And then on week 16, we have the final project presentation. Everyone clear with the schedule? Everything that we got left? So you just have left, present Sci 10 stage 1, stage 2 of the project, and then there will be a finalist. Yes. It's due, you have until the last day of class. So we'll start presentations on Monday, but you can still present on Wednesday. That's the last opportunity. Got it? And like I said, keep it simple. The goal is just to deploy a model with Onyx to the web with GitHub pages. Okay. All right. So yeah, so those were the ideas. Today we're talking about transfer learning. I'm going to do some examples of how to implement, how to use transfer learning now to solve Sci 10 essentially. Okay. So that's kind of the idea. So let's take a look here. So I'm going to add it probably here with resonance. Papers there, but seems like a good place. So I already added the code on the GitHub, so you can get it from there. So we got ETS 365, machine learning foundations. I have this little folder here called transfer learning. And there's a Jupyter notebook example there, so I'm just going to copy that. Link called code. So where you see resonance, that's essentially the topic. Okay. It's a PDF. Yeah, that's what I was looking for. So this is just some definitions. So we have something to work off of. I'll just add that here as well. I'll just call it PDF. Okay. All right, so let's take a look. All right, so this is, the code, and this is just some notes that I provided. All right, so we'll start. So transfer learning, right? So this is the idea for stage two. Essentially, you're borrowing someone else's weights, right? Somebody that has maybe a lot more images or data, a lot more computing power, also, a lot more people that can work on the problem and figure out the best way to approach it. So transfer learning is one of the most important developments in AI since transformers. Transfer learning is an approach where you pre-train a model with some data, usually a lot of data, and then fine-tune the same model with less data, but for a specific task. All right, so far you guys have trained your models for the Cypher 10 challenge from scratch, right? But now you're going to take a different approach for stage two. And that should, everyone is hovering. Quinn has the highest score at 83% right now. And is that, if you're just using those images and training from scratch, is that like the best you can do? Right. So that's what we're going to see like in real time, right? We're going to see if transfer learning can give us more. So this allows companies, entities with vast resources to pre-train models that they can later share with others. Okay. So such as in this example, we would want to use a pre-trained ResNet. Training with massively large data sets requires a lot of resources such as computing power, money, and can currently only be done by large institutions and companies such as Google, Meta, OpenAI, and so on. Right. So these are done by big teams. So here's some important keywords or ideas of transfer learning. Some of the most important ideas in transfer learnings include pre-training, fine-tuning, freezing some weights of the neural network, sharing the weights from one model to another, something called reinforcement learning through human feedbacks, and transfer learning tricks, right? RLHF is a topic beyond the scope of this course, so we're not going to cover it, but the other topics actually we will be using. So pre-training, let's talk about the first term. So pre-training is the process of training a model like a large language model on massive amounts of text data. In the past, the best models have been the ones pre-trained by large companies such as OpenAI, Google, and Meta. Pre-training starts with a model that has had no training and where the weights are usually initialized randomly. Essentially what you're doing in stage one. The process can take many months, require multiple GPUs, and training needs to be performed on distributed GPU systems. So ResNet, the ResNets can have ResNet 50 will have 50 convolutional layers. ResNet 100 will have 100 layers, and so on. Those algorithms are called residual networks because they also have a little trick that we'll talk about, but it's a very simple thing that solves a very big problem. So but in pre-training, you start with code such as that of a GPT algorithm or your CNN. You need to train a model for long periods of time with lots of data. That's the way you start with fine-tuning is the process of taking a pre-trained model with pre-trained weights and performing some additional training on it. Here you want to reuse as much of the pre-trained weights as possible. You don't really want to change those. We want to change the new layers towards the end of the network. So here we want to reuse as much of the pre-trained as possible. One scheme for this requires freezing layers of the network so that those corresponding weights are not changed during fine-tuning. So this is the term freezing weights, right? So you can freeze weights so that they not change. You and also just update the weights that's much smaller. So that's equivalent to taking a lower step, which updates the weights every little iteration. Fine-tuning hill, we don't know what to do currently, and they not require massive amounts of data. It's usually focused on specific tasks, sentiment analysis, question answer. So in your case, it's stage two, you have a very specific task. Classified images between 10. So here's an example of freezing some weights of the neural network. But before we find tuning, are the little ways of the process can be seen in the next code. So here we have a model. This is actually a transformer model of GPT. You grab the hidden layers, you count them, there's 12 in this example. And then calculate, you're going to um, figure out how many of the layers you want to freeze and how many of the layers you want to leave not frozen. So in this case, you have a 0.30 to 0.70 ratio. So here, once you have that, you have 12 layers in this variable here. So you're going to go from the beginning to 7, essentially. I think 7. So its number of layers is 12 times 0.3. That is 4. And then, so this is going to leave some of the layers not frozen and some of the layers frozen. So the trick is you iterate through all the layers from beginning to end. You grab each layer, so 4 layer in layers. And then you just have to change one simple parameter where you say layers dot requires grad, and you set it to false. By doing that, this is equivalent to when we have done for inference, right? So we just want to test the model. So we also set require grad to false. And that's essentially what it is. And this print statement just will now check which layer is frozen by printing the layer and printing if it requires grad or not. So notice that in the previous code listing, we iterate through all the layers and change the parameter layer dot requires grad to false. For all layers, we want to freeze. The result of freezing can be seen in the following for a GPT-2. So you can see that there. So you're iterating through the model, and you want to make sure that the network goes from input to prediction, right? So it goes from the first layers to the last layers. You want to freeze the first layers and leave the last layers unfrozen, so that those would be the ones that get updated during training. So here we have H0 dot 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 all the way to H8, H9, 11. Notice that 11 requires grad all the way. So everything 1 through 8 does not require grad, right? So it's false. And then starting on 9, it's set to true, which means those are not frozen. Do you guys understand? Right? So you have 12 layers. The first are frozen. So that means that you trust those weights that they're going to be pretty good at taking an image, extracting features from it, the semantic meaning. Once that gets to like layer 9, from there on, you can now change the weights for your specific task. This is a pretty generic approach. This is not actually the approach I'm going to recommend for Sci-Fi 10. We'll have another one, but this just illustrates the idea. So this one does not add new layers, which I think is probably better to add new layers. Sharing the weights from one model to another. So sharing weights is very important as it allows pre-training to be done only once. After that, only some modification to the weights needs to be done. In Torch, the weights can be extracted easily using, for example, model.parameters. So you guys have seen this part of it when we instantiate the optimizer. Currently, there are specialized libraries to help share models. These include Hugging Face, Transformers Module, or Fast AI. Today, I'm going to introduce the module that is allowed for the competition. Okay, which I think is torch vision. RLHF also, yes, this is obviously on the scope. And then these models that use transfer learning, they're models that are very smart, right? So these are, they can almost solve math problems today. So they have a new set of metrics that are more advanced than the ones that we have in class. Yeah, so that's just, a basic introduction to the topic of transfer learning, some of the ideas of it. So now let's go ahead and look at code. All right, so I'm going to do two examples today. Let's the table of contents. And just going to play with this one. Click on ResNets, click on code. All right, and this is the script that we're going to try out. We're going to try this one in Colab. Okay. Notebook. Cells. All right, so let's see. So some of the libraries here. So Torch Vision. So from Torch Vision, import transforms. This is one, if you remember, transforms are for modifying the images into tensors, resizing. Resizing here may be important given that we're going to use pre-trained image processing models and they expect specific dimensions. Let's just add that. Let's see if Torch Vision is available. Right, so it looks like it took it. Then I'm going to just the common libraries. So Torch, TorchNN, Functional Optim, Pill, Images, and Matplotlib. Simple. All right. And then here, now I have from Torch Vision transforms as transforms, which is as I said, for processing. And also this one, this is really important. This is the library that allows you to bring in your pre-trained models. This is the library that is allowed for the competition. The only one allowed. Does that make sense? Unless you use like Torch Hub also is fine. Questions about that, guys? Nope. All right. So, but yeah, so this from Torch Vision models has models. Now we're going to have an object that gives us some models to play with. So the first thing we might want to do is visualize them. So we're going to list them. So Torch Vision models is, a stat script. Let's view them. And there's a lot of models in there. So we're going to do dir models. Okay. And these are all the models that are available there. I don't know all of these. There's different variations, so you can see these are pretty important ones for your task. There's a ResNet, ResNet 101, ResNet 152. Keep in mind, those, even with a GPU, might be too big. You got ResNet 18, ResNet 34, ResNet 50. So it's up to you guys to figure out which one you're going to use for the challenge. You got ResNext 101. Have a segmentation model for image segmentation. I don't know what SqueezeNet is. VGG, that's another classic like ResNet model. So we'll talk about that one if time permits a little bit. There's several versions of VGG, so you can try that. There's these vision transformers. So these are models that use transformer models. So they're sometimes called ViT as well, but vision transformers. I'll actually give you some code for this, but it's up to you guys, right? To figure out which one's the best, which one, depends on your GPU and all that. All right, but these are some of them. So mainly ResNet is the one that we can play with. We discussed it so far. Look at the models. All right, so we can initiate something like AlexNet from here or something else. So really all you have to do is create a variable. AlexNet would be the classic neural network with two convolutional layers from 2012 from the image net competition. You can see the model. And there it is. So now the model has been loaded. So now this model, you can say if it's pre-trained or not. And then what you need to do is figure out how to get the inputs through it. And then once it processes an output, how do you map that to your feed-forward layers and your classification? Here we can look at AlexNet. So if we run AlexNet, you can see it shows you the architecture of it, all the convolution layers that it has, the dimensions. So this one seems to have five convolutional layers, right? Keep in mind from 2012 to now, GPU power and everything has changed significantly. All right. Now our ResNet. So these are very popular, as you may have heard. So we instantiate a ResNet from models.resnet101. Look at that. And you can say if you want it to be pre-trained or not. So you could actually pick one that is not pre-trained, which means the weights are going to be set randomly. And then from there, you can proceed to train it from scratch if you have enough resources. All right, you can see the models took a second to download. So we can try to print. And you can see this starts to give us the architecture for the ResNet. You see it's a bit more complex, longer. It's got a final linear layer at the end. Let me actually change the name. Call this in-class learning. Okay, so we've got the model there. So that was our ResNet. It's pretty big. Okay, so this is just an image. I guess I need an image. This big. Okay, grab that image. Yeah. All right, so let me download that. Should be in downloads now. OneDrive. Right, so just a file. Download. Okay, so that should be added now. We can go back to here, mount the drive. Drive. Yeah, there it is, dancing JPEG. Okay, so we can get the path of. All right, so that should be the image. All right, so we need some image to process this. It's that. All right, so let's read an image with pill. Okay, we're going to provide this one. Okay, it loaded the image. Now let's view it. IMG. And there it is. So we have an image of a ballerina. So now, just to illustrate the transforms. Transforms are these built-in objects from Torch Vision. We can create an object called preprocess, which is a sign from transforms, the compose object. And inside, we're going to add various steps. So one of them is resize. So you can resize the images. You can center crop the images to be 224. You can convert to tensor and so on. And these are just examples. You guys will have to refine this for your task and your specific models. Some models might need different things. So now we take the image. We want to print the size first. So we're going to do img.shape. Oh, it's a pill image. So yeah, it's not a torch tensor. We'd have to convert it, which we can. We have to convert it into a NumPy and then a torch tensor. But this will convert it into a torch tensor. So now we have it. Let's take a look. shape. And there you can see the image is now color image 3, comma 224, 224. Does that make sense, guys? So pretty important. So this is how you can process your images to be of specific sizes and so. Torch squeeze and unsqueeze. This is an interesting idea. So as you know, when you give an input to a neural network, it wants also an additional dimension called a batch. So usually it's going to be a batch of 32, comma 3, comma 224, comma 224. In this case, we only have one example, so we can just unsqueeze image tensor on 0, which means essentially that it'll add one additional dimension in the front. Do you guys see that? So it'll be 1 by, so if we do that, you can see it's now 1, comma 3, comma 224, comma 224. If I did unsqueeze 3, you can see it's 3, comma 224, comma 224, comma 1. You're just adding, you're like expanding that dimension somehow, right? But you only have the one value. So this is used sometimes when processing inputs into a model. But the correct one should be this one, which intuitively just means one image, a batch of one image, which is color and is 224 by 224. Okay. All right, so we've done that. Now we give one image to the ResNet. So I'm gonna put it in eval mode. So I'm gonna do ResNet dot eval. Okay, so it's an evaluation mode. Okay, and now we are going to run this. All right, so we ran that batch of one image, the ballerina, through the ResNet model. The ResNet model was trained originally on 1,000 classes. Okay, so let's see what happens. So you can see now the pred is essentially a vector of size 1,000. So it produced a vector of 1,000 classes, and one of them will have the highest probability indicating which class it says that this is. We're going to look at torch max. So we give it the vector pred, and it's going to select the highest probability, and that should be an index. So we want to look at index. 601. So do you guys understand what happened there? There was no training, right? I only did inference. I brought in a ResNet, which takes images. I gave it the image of a ballerina, and it just predicted that it's one of 1,000 classes. Obviously, you can't use this as is for the Sci-Fi 10 challenge. You'll have to modify, remove that last set of layers, put in your own set of layers, and fine-tune. But this is an illustration. So of that, we can also use the model assist, and it'll predict one of its original 1,000 classes. So what is class 601? Help me out. Go online and just look up what is the ResNet class 601. Let's see if it was successful. What is it? Well, I mean, we want to know what the class 601 is for from a ResNet network. So you can Google like what class 601 for ResNet network, machine learning, something like AI, and it should say it's just ImageNet class list. So that could also be. So you can go online, you can Google something like ImageNet class list. So here we are. Okay, and we need to find what 601 is. So it says it's something called hoop skirt crinally. So what do you guys think? Does that match hoop skirt? What is a hoop skirt? Maybe a hoop skirt is what she's wearing, right? Like that little, could be. You can Google it and find out the meaning of that word. But anyway, so this is a good example, right? So we got to the end of it. So you can see of the code example. So now let's kind of discuss. So I'm going to go to the whiteboard for this. Whiteboard. Okay. So here we have, so the example. So I used a ResNet. What was it? Was it a ResNet 50? Just a regular ResNet, but you can pick or layers you want by picking another model. All right, so let's go back to the whiteboard then. Yeah, so let's think about it. So I picked our ResNet network. Okay. Think of this as being all the convolutional layers. Initially, it takes an image, right? And just be aware that image needs to be resized. I think we resized it to 224 by 224, right? In the transforms, that becomes the input image to the network. Then it has this component here, which is just regular nn.linear functions, nn.linear. So it's just, these are called feed forward, but they're just a traditional nn.linear. And then these produce a vector, predict a vector of size 1000, which was trained on 1,000 classes. So with the image net data set, millions of those images went through the ResNet, trained this, trained that to predict one of 1,000 classes. Okay. That's why right now I was able to just grab an image from the internet, ballerina, feed it into it, and out came and it said that this was, 601 is the top class. Do you guys see that? So that's pure inference. Obviously, you can't use your model like that for the Cypher 10 challenge. So you have to make some modifications. So instead, what you'll have to do is so you'll have your image 224 by 224. That's the same size. It goes into the same ResNet. Same ResNet. But your target is not 1,000 classes, right? Your target is only 10 classes because you're doing Cypher 10. So you want to change, you want to basically like get rid of this and that, and you just want to preserve this part. Do you see that, guys? So these are usually called the heads. So you can remove those and replace them with your own. Just like that. And so these weights, you can freeze or update them very slowly. And these you can update faster or something like that. But these are the weights that need to change to correlate with this. Because right now, the weights in the ResNet correlate with its own classes, right? So it wouldn't work with the other classes. And so now you're going to take this model and fine tune it, but using the ResNet that you have loaded. Is this clear for everyone, guys? This is what you need to do, right? Any questions? All right, so now let's take a look at how we can approach that type of a problem, okay? So I'm going to go to, let's go share the screen. Okay, so we're going to share the screen. We're going to create a new script. We can actually continue that. All right, so this one is going to be, change, update the ResNet for your own data. Okay. So let's consider a new one. So let's look at the models that we had available before. So up here, we have let's take a vision transformer B16 or B32 actually. So let's take this one. Okay, so just the model, you can do this for ResNets, etc. I leave it to you guys to play with. All right. So we're going to instantiate a new model. We're going to say models dot vision ViT. And we're going to take the default weights for this model because we want a train set. So we're going to say weights. A lot of these will have different parameters, so you'll have to explore them. So weights are going to come from models dot ViT B 32 underscore weights dot default. Okay, well, let's see what happens. Okay. It's equals. Try to lowercase I there. Uppercase weights. Default. Right, so it's downloading, see if it's a slower one, but it's fast enough. So this is a big model. So you can do this with your, with your chosen model. All right, and now we have to think about changing the heads. All right, so the process should be to map the output of the input to the head of the ViT to a new layer, right? And the way that we can do that is to create a new model head. So I'm going to say model dot heads. So model dot heads, and it's going to be a torch dot nn dot linear. Okay. And now we have to specify kind of the inputs and outputs. So the outputs will be out features, and we're just defining a new one, equal 10. Why 10? Because it's the 10 classes of Cypher. Remember, this is at the very end of the network, right? So we are essentially creating that new one, and then the input to this will be kind of the output of the old model. So we can say in features, is going to be model, which is the ViT, dot heads dot head dot in features. It's got a nice parameter there to link things up. So let's think about it going back to the diagram. Okay, so what I'm doing is, right, the ViT has, takes an input, got the ViT, right? Then it's got all these 1000 or whatever it is, and it's got this input features, right? So it's essentially what comes out of this. Do you see that? And so what you're doing now is you're creating a new head that is 10, and you're going to link up that with that. Got it? So you're not going to use this anymore. So obviously this connection between this in features and the 10 classes has a whole bunch of weights, right? And those are the weights that need to be trained. And you can do that. You can add as many layers as you want. You can play with that. It's just a simple example, but that's essentially what you're doing with this code, with connecting the heads to a new layer. All right. So let's go back to the code and I'll repeat. All right, so I'm going to repeat here. So I create update, say the model, because it's not a resonance, this is a ViT. All right. So now I create model heads, right, which is a torch and linear that connects for the in features, it takes the model heads in features, and the output is just going to be these 10. Run that. Probably capitalized. Nope. And out features is misspelled. All right, and it took it. Do you guys see that? That's it. That's key, right? If you guys understood that, you're in pretty good shape. Because all you have to do is unlink that last part, create your own, and then you're going to do, obviously, the training. Whoops. I think it's because I had already ran it, and so the model lost its structure. Yeah. So don't run it twice. All right. Now that we've done this, we need to probably initialize the weights to some random thing and then print out the architecture. Okay, so let's go ahead and initialize the weights. So we can do torch dot nn dot init dot savior underscore uniform underscore and then we give it model heads. Model dot heads dot weights. So we just want to initialize, as I said, the weights of that head, not the whole thing. If you did that, then you've ruined the whole point of this. Okay. Oh yeah, it should be weight. Okay. There we go. All right, now we can print the model. And you can see this is, your transformer for vision, pretty complex. Notice at the end, you have 768 neurons that map to 10. Do you guys see that? So it's mapping from the network, what comes out of the network, to your 10 classes. And there you go. Pretty easy, right? Think about it. You've created a whole neural network architecture with transfer learning. Any questions? Yes, sir, please. Yeah. Which part? Okay. Yeah. Oh, print model. Yeah. Great. Great. So now that you have it, right? We have a model. We have to do a few other things, but we want to train it with our data. We have our Cypher 10 here already in Colab, so you guys should be able to run it. We're going to set it in training mode, so I'm going to do model dot train, model dot train, set it into train mode. Okay, that's fine. Always prints it. All right, so now comes the part with the learning rate. So the trick here, so in the previous example, I talked about freezing. So you freeze some layers and not freeze the ones that care about. That's one approach. The other approach that you can take is to have two different learning rates. You see what I'm saying? So two different learning rates. So a very, very, very tiny learning rate for the neural network from input to head. That way, all the weights get updated, but by very little. So it's not really going to change what it has learned from pre-training. And then the weights for the last part, the head that ties to the classes, have a bigger learning rate. So that way, when that learning rate takes effect, it's going to make big changes to the weights. So that's the idea. So we need to create an object called params that is going to hold a certain, one set of weights. So we need to separate out which weights will have which learning rate. All right. And that's going to be done as follows. So we need to, in Optim, so we're at the point where we need to define the loss function, the optimizer, and so on. Right. So I'm going to define the loss function first. And the loss function for this problem is what? Classification problem. Therefore, it should be cross entropy. Okay. Then, so I okay. Okay. Cross entropy loss. All right, so we got our cross entropy loss defined. Now I'm going to define for the optimizer, I'm going to use the add optimizer. So I'm going to set this as torch dot optim dot atom. Okay. And in the past, we have used this, but now we have to we have to define something called params, and we have to define what learning rate we want to use for that. We are going to have three objects in here. First, a list. Then we're going to have a learning rate, which should be the normal learning rate, or one of the learning rates. Let's call it the overall learning rate. And then we have that we want to use weight decay, which is like another technique like the scheduler that you guys learned about. This is yet another one, right? So decaying the weights. So weight K equal weight decay. This would probably work without this, but this is probably one of those parameters that helps out a lot. Okay, so just be aware of that. So weight decay has been added, looking for misspellings. Any? All right. So now in this square bracket is where we have to specify several things. We have to specify we need a list of the things that should have the bigger weight, the bigger learning rate. So we can do that as follows. Curly bracket, curly bracket. These are comma separated. Okay. And we're going to create an object called params here. So the key for this dictionary is params. And then we're going to give it as a value a list called params that we need to create. So we need to go through the ResNet or the Vision transformer or whatever it is and kind of grab the layers that belong to the head and put them in this variable called params, okay? So that's one of the things we need to do. We haven't done that yet. Then we need to specify for this params how to tie it back to the architecture. So we're going to say params colon and then model dot model dot heads dot parameters like that. Okay. So we tie it back to that and we specify the learning rate, which is going to be LR. And this learning rate is just going to be 10 times bigger than the other learning rate. Do you guys see that? So while the very tiny one is barely updating the weights, this one really updates the weights of that head section. So we can achieve that just by saying LR times 10. I mean, there's no science in this. You got to play with it, but this gives you an idea. This has worked in the past. Do you guys understand? All right, so we're just grabbing the weights as parameters. We're going to tie these back to the model for the head section, and this is the learning rate that we provide. So this other learning rate we need to define somewhere, but it's going to be, something small of our choosing. And if I haven't made any mistakes, this should be it. Yeah, I think that looks correct. All right, so let's run it. I don't have params yet, so it's going to error out. So I need to define that actually. Okay, so I'm going to define params here. So we know that params is associated with the head section. Okay, so let's go over here. Yeah, so actually, let me make a correction to what I was saying. This makes more sense now. This param corresponds to this learning rate. So that's going to be the params that is not the head section. And then this head section corresponds to this learning rate. Do you guys see that? So that's why you do it. So think of it, that's what so usually we would, in this field, we would usually specify the model parameters, right? But we have to separate it out. So I'm almost positive that this is tied with this one, and that's why this one has its own learning rate there for just the model head parameters. And they're both params. Because if when we create this param, you'll see what I'm talking about. So we're going to create a list comprehension. And I'm going to say param for name, comma, param in model dot named parameters if you can see this if is really important, right? So we're iterating through the model, not through the model head parameters, but through the model name parameters. So everything, right, in the model. So all the parameters in the model, we're grabbing the name and the param, and we're adding it into this list only if heads not only if heads not in string name. Do you guys see what I'm saying? So I take it to mean it's grabbing every layer, right? The first few layers don't say heads, right? So it's only grabbing those. And then when it grabs one layer that says head, it's not going to add it, right? So it's saying, from model name parameters, add param if head's not in string name. Everyone with me? Okay, great. So then you have these that are not the head. You add them here, and they would be linked with this learning rate. And then you create this other dictionary in here, but this one has its own learning rate, right? So maybe you could argue if it doesn't have a learning rate, then use the default overall learning rate. Whereas this one has its own specific one, LR times 10 for model.heads parameters. So only those layers at the end of the network that are the ones that we want to change. And if this is 0.001, this will be 0.001 times 10. So bigger, which would have a bigger impact during training. All right, so let's try this one. Okay, got an error. I'm missing the parentheses here. Okay, that worked. Now, this one over here, that one gave me an error as well. Oh yeah, we haven't defined the learning rate. We can just define it to be anything. So let's just take anything here. LR equal 0.001, something like that, right? You can play with that. So now we should have so let's try it again. Weight decay is not defined. So this is probably a parameter we needed to define. I'll just leave it out for now. Okay. All right, there we go. So we've got our optim, we've got our torch. So the params variable is all weights that are not the head. In the optimizer, the learning rate could be even tinier actually. So let's do, because it might have a big impact actually. 1.001 is the default, and it might be too big. So let's go with something smaller. So 0.001. Do you guys see what I'm doing and why? Right? so it doesn't affect the non-head layers that much. So make that learning rate smaller. Questions? All right. So now, okay. Yeah, let's load this again because I updated that learning rate. Okay. And now we should be ready to start training. Right. So we need a training function. We got our architecture. We define. So we would need something like this, right? So we've instantiated the model. We've created the loss function. We've created the optim. So now we would need a function such as this one. Okay. Training loop, number of epochs. We'll need to define that. Model we have, loss function opt for epoch. We obviously need the data and the train DL. That's, something that you guys already have. Run it through the model and so on. Do you guys see that? So that's essentially the idea. So we'll need to borrow from this code to integrate it to Cipher 10. And then this is how we would invoke the function. Down here. But we're going to need to do a couple of things. So now we're going to add the data set. We probably need to change to GPU as far as the environment is concerned. I'm going to remove some of these. All right, so we did this. So let's take a look. Add some more libraries in case we need them. Train test split, all that. Search eval. Gonna comment that out. All right. I gotta print the models. So then we need I created this as a collab, didn't I? I can just use that. Where did I put that? And I thought I loaded it, but maybe I didn't. So we'll just redo it. All right, so this is we already have those. We need the data. We need to use the drive. So it's I guess I don't have Cypher. Yeah. So I was using fruits, right? Fruit Cypher. Yeah, banana and pepper. I'll have to use that. Okay. I'll do that here as well. Okay. Got the libraries. And that. Gonna remove Alex now. Checkpoint. Sure. So this is going to be in my drive, maybe. Okay. Hit run. All right. Here. Then we need to do this. Get the training data. This one. Okay. So let's try that. So this is, I'm just repeating what we had done before. If you're processing, this will just have two labels. And it finished, so we got a green one then. I'm not using this ResNet. I already demoed that. So if we print, there should be two. There we are. Okay, images, I think it was like 700. We can print a shape. And that's 3 by 100 by 100. So that's all pretty much what we had done before. Then we're going to create the data. So data train, torch stack, data set train, targets train, torch tensor, targets train, long tensor. All this should be the same. Okay. Print the shape, all this, we can print the images, look at an image. We can skip this for now, class imbalance. This was for the test set, which we don't need during training, if I remember correctly, so I can skip that. This is all test, all that. Fix the float thing, so probably this part we do need to do. Okay, rename things. Skipping on the test set for now. This is all train. Hit run. Okay. Oh, the test. So it only does. Okay. Okay, so on that. Strange. I think I had already renamed these. Oh, okay, there it is. Yeah. Okay. So now normalize and pre-process. The resize we might want to do. Transform resize, center crop 224 to tensor, and then X train. I'm going to use pre-process. Change this to pre-process. Okay. Mhm. I guess it's already a tensor, so let's see how we can handle it in a different way. Uh, we should be close. All right, and this is where you create the list. Did that. All right, now create the data loader, so we need a batch size. That's a lot of steps. We need to create train DL. Okay. So we have our train DL, and that's the architecture. So then we have the train loop. This view, I'm curious if I have to do the resizing here. So that's the one part. I'm not sure. We'll see. But yeah, so we would run it essentially. Okay, so the model. Okay, finished. Then the thing with the heads, create the head. Done. Update the weights. Print the model. The big model. Model train. The loss. The thing with the params. Opt. This is the train function, and here is we kind of have to figure this out. But then this one here. Okay, so it gives, oh, and that fix is not defined. 10. Name torch device is not defined. So I haven't defined. Well, let's just use CPU for now. I'm just gonna make sure this works. All right. See that, guys? So here's the issue. But I was saying everything, I think it's in good shape, except that the image is 100 for that image data set, and they need to be 224 because that's what this model is expected. So we need to do that conversion somewhere where it's convenient. So I tried to do it with the pre-process, but it didn't let me. So when we were doing the reading here, the images are 100, image read from mute. This is a pill image. I think where do you guys see what I'm saying? This is the last bit of this. So this is the see, this is where I try to do it. Resize. I just need to resize to 256, center crop to 24. Something like this. That's something in the see what it's not liking. I actually don't know what it's not liking because it said pig should be 2 3 dimensional, got 4 dimensional. Okay. It's already a tens. Oh, okay. So it took that, right? No errors. Okay, so then I have to redo this. That should be fine. Okay, so something. Let me one. Any questions, guys? It's good actually that the dimensions were not compatible because you get the problem, right? The problem is the images were 100 by 100 in my example. The rest or the whatever this model is wants 224 by 224. So you'll have to do things to convert them to that. I'm hoping that it is training. I guess we have a few minutes to switch over to the runtime. It's a little bit faster. Okay, we should be in GPU now. Okay, so I'm gonna just run the whole thing. Okay, finish that. Get that. Uh, and, all right, just reading the images from the fruits data set. And uh, get that. Yeah. Get that one. So loading the model again for the GPU. Heads as we talked. Save the model. Train. Loss function. Params. Opt. The loop. Let's give it a minute there. See what happens. Oh, CPU. Yeah. All right. Come on. Okay. This is a big model. Transformers. Like maybe don't do it. Transform. Just I'm trying to see if it starts printing out the losses or something. yeah, that's the essence of it. Okay. So go over this, obviously play with it. But yeah, don't start with this one, maybe try to rest in it, and that should be the main idea. All right, we can discuss on Wednesday. I'll play with this a little bit more. You have at least something to get started with stage two. Remember, this we do a week from Wednesday. That's going to be translating part of this. All right, guys. So it's 3:40, so we can stop here for today. I'll see you on Wednesday. Well, yeah. Just hold on. That's what I do. Now, yeah. Yeah. Yes, please.
So, when are you gonna post these description about the project on what needs to be done here?
Well, like I said, I can put it. Can you send me an email to remind me, and I'll. I thought it was there, but
No, yeah, I checked it on the content on the MySpace. We got to see it.
That's why I got that. All right, what does that say? Apply your machine learning knowledge to solve a problem we're choosing, must be approved by instructor, select a topic, get some data, train and test a model. In general, it will most likely be a classification or regression. In PyTorch only, you must deploy on GitHub with Onyx. Code, you will need to demo, do a presentation, submit a report of your findings, group of two, and here's some cybersecurity data sets.
So, is this where we'll be able to see this on your?
This is on Brightspace. Is this clear enough as far as what you need to do? Minimum two, no more than three. But otherwise, as I said,
Like a bottom of the section where
but you found it now?
Oh yeah,
Yeah.
yeah.
So just that.
And then one.
Yeah.
Giving for the presentation.
Okay.
So
Did I not grade that?
you did.
Okay.
So is it still part of the? Is it like part? Is it like still part of the grade?
If it's bonus, it's like one additional lab.
Oh, okay.
So if you missed a lab, then it replaces that, or if you've done every lab, I guess I'll consider it.
Okay. I just want to make sure.
But for bonus, yeah, if you have a zero, if it says bonus, it's bonus points.
Okay. Yeah, I just want
It doesn't count. Don't go by the grade book because I export that into Excel and do it manually.
Yeah,
So
because I remember you doing it.
I don't know how to use that.
I mean, I never just screen.
Yeah, don't. Just wait on. Oh, you have to do it manually if you want to do it.
Because I
Look at the
remember,
syllabus, do the calculation.
The bonus.
Yeah. Yeah, I always do at least one bonus lab.
Because I didn't, you didn't like, I thought you'd be doing the bonus one toward the end of the semester, like you did for.
Yeah, I guess, yeah, I see what you're saying. I don't have a bonus right now because you have a lot of work already. I don't want to give you another.
Final.
Thank you.
All right, yep.
After room.
Oh, yeah.
Oh, man, I don't.
Oh, it's still is. Yeah. Audience would be fine, for like over 4 hours, like yeah, it's sort of 5, 6, but it looks like so there's not even hard to, but the actual, yeah, no, the bicycle library.